Okay, so the if we're looking at an object that's in orbit, we can assume that, or we can approximate what's going on in terms of circular motion. So we have this object in orbit going around the Earth, and we can approximate a circular path. We can look at the sum of the rotational forces equals mv squared over r. We know that the centripetal force is the force of gravitation here. So this is the force that is, keeping the object in orbit. M1 is the object itself. Whatever this is the object that is going right here around the Earth. And so we can cancel the mass of that from both sides. We'll call the satellite M1 here, and we can cross multiply and simplify. And so this would give us the approximate orbital speed, assuming a circular orbit, where we're looking at the mass m2 of the Earth in this case, how far away we are from the center of the object to the center of the Earth, and we can figure out approximately how fast it's going. So let's go ahead and approximate the orbital speed of the satellite, and we have these values here of the satellite and the mass of the Earth. Go ahead and hit pause and calculate this out, and then when you're ready to check, you can hit play to continue. Okay, so you should get, for our values here, we cross multiply gm2 over r. We should, for our radius, you have to get that into meters, so about 4,440.73 meters per second is how fast the the orbital speed would be for the satellite at that altitude. All right, so if we think about the orbital speed here, and let's assume that we make a full circumference in a certain amount of time, we can set those up together. We can go ahead and square both sides just to make it a little bit easier to substitute. So we have these values on both sides. We can solve for the period, and we can do that here through our algebraic steps. And so this is how we would find the period of the object as it goes around. Again, approximating a circular orbit. The period squared equals 4 pi squared radius cubed divided by gm2. So the orbital period of planets around the sun is proportional to 3/2 power of the radius. So in other words, if we're looking at an orbit here, let's say this is the sun, and let's say we're a certain distance away here, right? Let's say an object versus the one that's further away. As we increase the radius, we're also going to significantly increase the period as well. And so this directly relates to Kepler's laws, where this proportion works. And and so we have this general pattern, and that will always be true proportionally. And then still, the mass of the object is going to matter, right? And but between those three, right, you have the orbital period, you have the radius, and then you have the object itself. Between those, you can figure out what's going on with the objects around the central object in orbit. Okay, so here we have two set of Saturn's moons, and we have the orbital radius of Titan and the orbital radius of Enceladus, and we have the angular speed. We want to find the angular speed of Titan. So see if you can figure this out based on what you've learned so far. Let's go ahead and establish our two objects here, Enceladus and Titan. And so, go ahead and pause the clip, see if you can figure this one out, and then you can hit play when you're ready to check. Okay, so for this one here, the linear speed we can get from the first one here from Enceladus. We can place this in here and end up finding what the mass of Saturn is. And once we know that, we can find out what's going on with Titan. And that's the linear speed of Titan. We can calculate the angular speed then in how many radians per second.